Okay, we're back to talk, to wrap up with buoyant force. So, last time we put an asterisk next to what happens if the density of the liquid is greater than the density of the object. We said that the object will accelerate upwards until it's floating. Well, let's take another look at that case. What if we have an object that has floated to the top, not this time completely submerged, but instead partially submerged? You can imagine that this is going to be a little bit different. So, a couple things to realize. Less water, or less fluid, I should say, less liquid, is being displaced, which is interesting. Okay. Before, when the object was completely submerged, you can imagine it was displacing an amount of water equal to its entire volume. If it's floating, it's only partially submerged, then not as much water is being displaced. Also, because the top and the bottom of the object they're not completely encased in fluid, the pressure differential between the top and the bottom is probably less. The pressure difference between the bottom and the top is less. So it would stand to reason that the buoyant force would be less. Less buoyant force is needed to support the object. Turns out that the actual formula for the buoyant force is as follows. Buoyant force is equal to the density of the liquid multiplied by V, I'm going to just do DISP times G. That's the equation we're going to go with in general for the buoyant force. V DISP is the volume of the liquid displaced by the object. Okay? Notice that the buoyant force has nothing to do with the depth of the object, okay, under the surface. It is only due to, the buoyant force only depends on three things: the density of the liquid it's in, the volume of liquid that it's displacing, and the acceleration due to gravity. Okay? So if an object displaces more liquid, then it's going to have a greater buoyant force on it. The buoyant force ends up not being able to fully support the object when the density of the liquid is less than the density of the object. I've got one more little example to show you with this, and I think it's kind of a neat one. And it has to do with this. How to tell the density by how much of a floating object is submerged. Let's do a free body diagram. For a floating object, we know that the buoyant force would point up, the force of gravity would point down, and we're going to say up is positive. Very familiar net force equation. In some of the problems you'll see we might have strings attached to this object, or someone is pushing them up or down. So your free body diagram will not always look this simple, but the buoyant force will always point up, force of gravity will point down. It's up to you to determine the direction of the other force. If it's floating, let's assume that it's staying there. So therefore we have the density of the liquid times the volume of displaced liquid times G. On the other side, bring that to the other side, mg. I'm going to cancel the g's actually. And we're going to bring this to the following. P liquid, V displaced equals the density of the object times the volume of the object. We're going to make a note of this. If we want to tell how much of the floating object is submerged, then we can say the following. V displaced, the amount of water displaced, is equal to x times the volume of the object, where x is some fraction. In this case, x will be the percentage, let's see here. X is the fraction of the object that is submerged. Then we can say the following. The density of the liquid multiplied by x times the volume of the object equals the volume of the object, or the density of the object times the volume of the object. Look what just happened. I now have V object in two different places. I can cancel them. And if I solve for x, I get that the percentage, or the fraction of the object that's submerged is equal to the density of the object over the density of the liquid. And that makes sense. If the density of the object is equal to the density of the liquid, then x is 1. That means that the entire object is submerged. If the density of the object is half that of the density of the liquid, that means that half the object is submerged. We can determine the amount of the object that's submerged, x, from some very basic length measurements, volume measurements. And then, if one density is known, we can calculate the other. So this is a useful tool for either determining the density of an object that is floating in some liquid, or the density of the liquid itself. We just need to know the other density and the proportion, the fraction of the object that is floating. All right. Switching gears, that was all what we could call hydrostatics. We're now going to switch gears and we're going to talk about fluid dynamics, which is the study of fluids as they actually move, as they flow and move. We're going to start by talking about the volume flow rate. The volume flow rate and the equation of continuity are very similar topics. Definition of volume flow rate is the amount of fluid flowing past some point per unit of time. I'm going to draw a picture for you. So here's a pipe. Usually when we're dealing with fluid dynamics, we're dealing with pipes. And let's say that we have some plane of water, okay? So some area of water in here. It doesn't have any density to it, or it doesn't have any volume to it yet. It's just if you were to basically a cross-sectional area. We're going to label that A. And that if it's in this pipe and flowing, then that cross-sectional area, let's assume that all the points in here have the same velocity, V. Well, in a certain amount of time t, then that area is going to flow through this. All the water particles right here are going to flow through a certain distance in this certain area. And what that means is they're going to move through some volume. If you take this area and you let all the particles in here move this way, it's flowing through some certain volume. Okay? And that volume, in other words, the volume flow rate, is given by this. Q equals A times V. The volume flow rate equals the area, the cross-sectional area of the pipe, multiplied by how fast the water is flowing, because that will determine how much volume of water passes by a certain point in the pipe in a certain amount of time. So A is cross-sectional area of pipe. V is, and we've been saying water, so I'm going to keep saying water, the water flow speed. I want to show you one other way that you could calculate Q. Q is also equal to the volume of water divided by the amount of time. Okay, so there are two different ways to determine this. If you were to say that so this is volume, so I'm going to do capital V. Let's make sure that's clear. This is lowercase for velocity. Remember, volume is equal to area. In this case, if this amount of water is moving through some certain volume, then it's equal to area times how far it moves, which would be A times D. And if we have AD over T, then D over T is equal to V, and we're back to this. Q equals AV. Volume flowing past a point, V, capital V, in time t. Okay. Essentially what this boils down to is you can calculate the volume flow rate of something usually by taking the cross-sectional area of the flow multiplying by the flow speed. Many times we're dealing with circular pipes. So Q is equal to AV. The area, the cross-sectional area of a circular pipe would be the area formula for a circle, which is pi r squared V. Sometimes you're even given the diameter, in which case r is d divided by 2. So we end up with pi d squared V over 4. Okay, those are different ways to calculate the volume flow rate. Let's talk real quick before we get into equations of continuity about why does fluid flow? Why does it flow in the first place? Well, assuming uniform density, which is pretty much the same thing as assuming what's called incompressibility. If that wasn't the case, then fluid could, I guess we would say, back up. You would get fluid kind of bunching up. And that doesn't really make sense. That, first of all, it's not what happens. The fluid would back up. If this were the case, if this did happen, then as the fluid backs up, as you kind of squish more and more fluid into the same volume, then that fluid, because there's more particles there, it would exert a greater pressure. It would want to expand again. Okay? If you squish something down past what it wants to, past the volume it wants to be at, it will try to expand back outwards. So if that wasn't the case, fluid could back up and would create a pressure difference between high and low density and pressure. And this pressure difference, okay, would eventually be kind of transformed into a force, okay? Because there's a pressure difference, there will be a force that would push the fluid toward the lower density or pressure, which restores uniform density. So in other words, it's kind of self-correcting. If you have some amount of fluid that gets backed up, it gets essentially, if it would get compressed, and then because of that compression, we would get greater pressures in that region and lower pressures in other regions, so the fluid would get pushed back to those regions of lower pressure, and everything corrects itself. So even though we're assuming uniform density and incompressibility, even if we didn't assume that, that would be the natural state of things. Okay, we would end up getting back to where we started. So what ends up happening is, because we have uniform density and incompressibility, we don't have these bunch-ups. And what this means is that the volume flow rate is constant for all locations in a flow. I'm draw another picture here. Okay. So let's say we have some very tiny, very skinny area here. We've got some volume of fluid right here. And in this section of the pipe, this volume of fluid has, well, it's in a section of pipe with an area of A naught, and it's got a speed of V naught. And if we're going to assume that the fluid doesn't bunch up, that means that the amount of fluid flowing past a certain point has to be equal at all points in this pipe. And what that means is that if we then change the size of the pipe, that must change the speed. In other words, here's its different section of the pipe with a cross-sectional area of A. The speed must be much bigger. If the fluid from the first part of the pipe and that section of the pipe has a cross-sectional area of A naught and a speed V naught. If, let's assume, this amount of water as it flows down the pipe were to flow with the same speed here as it does here, then because this is a smaller area, there's a smaller pipe down here, if it was flowing at the same area, you would get a whole bunch of fluid, essentially, that gets kind of backed up. And what that would cause, if we're taking all this fluid flowing through this smaller area, you would essentially be compressing it more. And so what would happen is that would create higher pressure and it would push this water out faster. We're to move at same speed V naught in the smaller part of the pipe where the cross-sectional area A is such that A naught is greater than A, the fluid would compress. Okay, Okay? You've got something moving at the same speed but a much smaller area. That must mean the fluid compresses, but we know it doesn't happen. We know that that doesn't happen. So what must happen instead? Since this doesn't happen, the velocity must increase so that V is greater than V naught in the smaller part of the pipe. However, since Q, the volume flow rate, is the same throughout the pipe, the total amount flowing past any point is constant. And if we want to say that mathematically, then we would do that like this. Q naught equals Q, A naught, V naught equals AV. That is known as the equation of continuity. It says that the smaller the pipe, the greater the speed. Okay, and the volume flow rate for a given pipe is constant regardless of the size of the pipe, if it widens or narrows. I'm going to stop this video there. We'll talk about Bernoulli's equation, Bernoulli's principle, in our last video, and we'll see what Bernoulli's equation is. Okay?